this section will certainly make us think. All right. Sine and cosine graphs. Let's look back here at this unit circle idea. So again, imagining we're on a coordinate plane. And remember when we had quadrantal angles, we said we could figure out the value of sine and cosine by using these points, 1, 0, if I was right up here, 0, 1, back here would be, didn't leave myself enough room, -1, 0, 0, -1. And then we said, when I had an angle at any point on the unit circle, the ordered pair was the value of cosine of the angle, comma, sine of that angle. Here's my angle coming around right there. So let's think about that. If the y value is the value of sine, then if I start at 0 degrees or 0 radians, the value of sine is 0. And so if I come over here on this graph, if this is my angle, and you notice it's 0 pi, 2 pi, so I've done it in radians down here. But starting at 0 radians, the value of sine is 0. Then as I come around the circle, well, it's the y value, which keeps getting bigger and bigger until I get up here, it's all the way to 1. And that's pi over 2 for that angle. 90 degrees is pi over 2. So that would be right on this location. I'd be all the way up to 1. And then as I come around, that y value for this angle would be getting smaller and smaller and smaller until when I arrived over here at pi radians, it's at 0. So when I get to pi radians, it's at 0. And then if I keep coming around, that would grow and grow and grow until it got to -1 in size. So -1 in size. And then I keep coming around, and the y value of this angle, wherever this angle is, that y value is getting smaller and smaller and smaller until I get back to 0 again. Until I get back to 0 again at 2 pi. And then it would just keep repeating itself as I go around and around and around. So if I just connected this with a nice smooth curve, which would match all the points, there is my sine graph. Or we call it a sinusoidal curve. And I'm going to pull up an animation of what we were looking at right over there. Oh, I want to get rid of, oh well. So I have this equation, g of x equals sine of x. It's on the wrong page. There we go. That's what I wanted to do. All right, here is my unit circle on the left, and I'm going to animate that angle right over here. So here's the angle. It says how many radians. It'll be a half a radians when it gets to the top. And this is the length of that y value, which is the sine value. So there you can see it now. It's down under the negative side. Gets down to -1. And then gets smaller and smaller and smaller. We get back to 0 there. Then it goes on the positive side. So if we went back to 0, and now I am going to trace the value of y. So my horizontal axis is going to be the angle, and then y value is going to be on the vertical axis. So it's starting, there's a little red dot right there at 0. Now I'm going to animate that. And you can see that angle as it gets to pi over 2, and there's that point, and the value of the point. And you notice the shape that it's making?
It's like a wave in the physics.
A nice sine wave, it is. This really ties into a lot of physics stuff, is exactly right. And then when I get to 2 pi, I'm back to 0, and I just repeat myself over and over again. And this is the sine function. There it goes. There's a sine graph, and it's just following the sine graph. And it is periodic, so it goes in the positive angle, negative angle, just keeps on going forever. So that is the sine graph. So we'll stop that thing and come back to, there we go. So let's look at the evaluation of all the specifics of this sine function. So our function is sine of x. The domain, all real numbers, all positive and negative angles I can put in. The range is from -1 to +1. That's as far as it goes, including that. It's continuous. Increasing and decreasing, well, it alternates. Increasing, decreasing, increasing. It just keeps alternating. It's symmetric with the origin. Rotate this 180 degrees and it falls back on itself, so it is an odd function. It's bounded. We have an upper and lower boundary. We have absolute maximums and minimums. +1 is as high as it goes, -1 is as low as it goes. No asymptotes to it, horizontal or vertical, none of those. End behavior, well, the end behavior does not exist because it does not, or the limit of it does not exist, because it doesn't approach a value. It's going up and then it's coming down, then it's going up, so it doesn't approach anything. It just continually oscillates between -1 and 1, so it approaches no limit. Now let's come back and look at the cosine function for a minute. If I come to this picture, remember cosine is the x value. So if I thought a minute about the x value, if I start here at 0 degrees, well, the length of the x is 1. So at 0 radians or degrees, I have a cosine of 1. So when I'm a 0, I'm a 1. Then as I come around, and we're coming around this way, that x gets shorter and shorter and shorter and shorter until it's at 0. At pi over 2. And then I keep coming around this way, and that x would get longer and longer and longer until it gets to -1. And then it gets shorter and shorter and shorter until here it's at 0. And then it gets longer and longer and longer as I keep coming around until it's back to 1 over here. There is my cosine function. We call it a sinusoid as well because it's the same shape. We call them both sinusoids. The cosine function, here is it, starting at 1 when we're at the origin. Notice the sine graph starts at 0 when we're at the origin or a 0 degree angle. So if I was going to analyze that, it is domain all real, same range, it is continuous, alternating, increasing and decreasing, but it's an even function because it's symmetrical about the y-axis. It's a mirror image if you flipped it across the y-axis. It's bounded, absolute maximums and minimums, no asymptotes to it, and again, there is no limit to the behavior because it just continually oscillates between -1 and 1. If I went back, because it's so cool to watch this thing over here, let's look at the cosine curve. Remember, the cosine is the value of the x. And if there we go, I come around with different angles, my x, it went to 0. And then it's growing in the negative direction to -1. And then it shrinks back down to 0. And if we watch that thing go, I didn't start it back at 0, but you can notice there I'm coming around to 1. We're going to jump back to the beginning now. I'm at 1. So here's the cosine graph. It's so cool to watch that smooth, perfectly smooth curve go along. So the sine and cosine are very similar to each other. Many, many, many similarities. They start at a different value at 0 radians, so they're moving at a slightly different value. Same range, -1 to 1, exactly the same range. A function is a sinusoid if it can be written in this form. F of x equals, you notice we can put a number in front. We know what happens when I put a number in front. It's a vertical stretch or shrink. I'm going to look at this plus c. I can add or subtract a number on the x. That's left or right translation. I can add a number on the end. When I add a number on the end, slides it up, translates it down. I can multiply my x by something. Remember, that's a horizontal shrink or stretch. definition of the amplitude of a sinusoid. We have specific names that go with these transformations when we're talking about sinusoids or trig function graphs. The amplitude of the sinusoid is absolute value of that number. So if we have 1 sine x, that's what we were looking for. That's what we were looking at just a minute ago. These are 1 times the sine of x. The amplitude is 1. The amplitude of a wave is defined from the equilibrium position to the maximum, or equilibrium position to the minimum. Both of those are a distance of 1. The amplitude of a wave is not minimum to maximum. That distance happens to be 2. That's not the amplitude. It's half of that. So the amplitude comes from that number in front. These happen to have 1s. Their amplitude is 1. Whether it's a sine or a cosine, it works the same way. The amplitude there is just the absolute value. Now, if I had a negative in front of it, what does a negative do in front of the graph? Reflects it across the x-axis. It won't change the amplitude, it just reflects it, rotates it across the x-axis. Okay, so that amplitude things are really vertical stretches and shrinks, is what the amplitude is. So it says find the amplitude of each function, use the language of transformations. The language of transformations are it's been vertically stretched, it's been vertically shrunk, to describe how the graphs are related. Well, amplitude. Amplitude of this one. Tell me the amplitude of y equals cosine of x. Amplitude is 1. Number is 1. B, what's the amplitude of this one?
1/2.
1/2. Now, this one has no change to it. That's just the parent function. This one has been vertically by a factor of 1/2. Half as tall, vertically shrunk. C, tell me the amplitude of C. Careful. 3 is the amplitude. 3 is the amplitude, absolute value of it. It still has an amplitude of 3, but it has been reflected and vertically stretched by a factor of 3. And I need to say how it's been reflected, because we can reflect across the x or y. Reflected across the x-axis, and then we have a vertical stretch by a factor of 3 times as tall. So tell me the color of graph that matches with each of these. A, what is the parent graph? Which color?
Blue one.
The blue one. The blue one, it has an amplitude of 1. Now notice this is the cosine graph, and the cosine graph starts at 1, right at 0 radians. Which color is B?
Red.
The red one. It's been vertically shrunk. It's half as tall. And then, well, the only thing left is the black one. Notice it's 3 times as tall. The amplitude is 3. Right there. There's my amplitude. That's 3. From here to here. That's where the 3 is measured.
Last question, if the functions reflect, is that equal to the original function move right or move left to pi?
Well, it can look the same moving it left and right. You're exactly right, because these things repeat. Now, this has been reflected across the x-axis with that negative, so instead of this black one starts down here at -3 instead of being up at +3. But you are right that, hey, if I took this point, normally it starts back here at the origin, at the y-axis. It's just been moved a certain distance, and it would look exactly the same. You're right. We're going to see that too. There's more than one way to make it look like that black graph, because it repeats itself. So let's go to that repeating stuff, the period of a sinusoid. The period of a sinusoid is found by this formula. You want to memorize that formula. 2 pi divided by absolute value of b. Now remember what the b does in the language of transformations? When I'm multiplying a number by the x, that's a horizontal stretch or shrink. And the period is defined in how long it takes to go through one complete cycle. If I go back to the original, right back here, from this location to that location, is one period of that sine graph. It has gone through one complete cycle. It repeats after that. How many radians did it take to go through one complete cycle? You can even think of the circle. 2 pi. It takes 2 pi radians to go through one complete cycle. And that is where this 2 pi comes from on this formula. 2 pi divided by b. That is going to be the period. Whether it's sine or cosine, both of them have the same formula because both of them have the same normal period of 2 pi to them. And depending on what that b number is, stretched or shrunk, well, the period changes, how long it takes to complete one cycle. So let's look at this horizontal stretch and shrink stuff, which we refer to as the period. Just like the vertical stretch and shrink stuff, we refer to as the amplitude. So find the period of each function, and then we're going to use the language of transformations, the horizontal stretch and shrink language. A, if I want the period, I go 2 pi divided by d. What number is right there? 1. The period of this one is 2 pi. There is absolutely no change. This is the parent function. There's no change on that one. B, if I want the period, I'm going to go 2 pi divided by 1/3. That's a 1/3 x if I pulled the number out in front of that x. Which means I'm multiplying by 3, which is 6 pi. So it's been horizontally stretched out. Remember, if I multiply by 1/3, that's 3 times as wide. Remember, it's kind of backwards when we do the horizontal stuff. So it is horizontally stretched by a factor of 3 by a factor of 3 times. Which in the language of periods, the period of this being 6 pi, it's going to take a full 6 pi before I go through one cycle on this one. It's really stretched out. C, 2 pi divided by 2, because it's the absolute value of the b, which means pi. Well, I'm multiplying by 2. Let's just look at the 2 part to it. It's horizontally shrunk. It's going to be 1/2 as wide as it used to be. So it only takes pi. It only takes half as far to get through one cycle on this one. Now, what does the negative do on the x? Reflects across the y. Now, I need to back up because I didn't say all the things back here. I didn't talk about this. That's old stuff. Not only is it horizontally stretched by 3, it's also been reflected across the what? This part B.
This x-axis.
Across x-axis. And it's been vertically stretched. Vertically stretched by 2. And this one down here has been, I'm going to start at the beginning, vertically stretched by 3. Vertical stretch by 3. You heard it, so you can interpret my horrid writing on it. What has this negative done? Reflected across the y. And it has been horizontally shrunk. It's going to be 1/2. Let's see if we can recognize for me. Can you tell me the original? A. Which color? The original is A. Now, you have to know right here the scale. So we have, let me see if I can write out the scale. Right there is 1 pi, right there is 2 pi, right here is 3 pi. So we know the scale that's going on. So the original, and this is a sine function, which starts at 0, there's the red line. Goes up, goes down, completes one cycle in 2 pi, right here. So that's the original one. All right, how about B? Which color is the B? Right? 6 pi. It's going to take a full 6 pi. from negative 3 pi all the way to positive 3 pi before it has completed one cycle. There it is. It's the blue one. It's taken a full 6 pi to complete one cycle out of it. It also has been reflected. Notice the red one, we start at 0 and go up. This one is starting at 0 going down. It's been reflected, been turned upside down. And 2, an amplitude of 2. There's an amplitude of 2. 2 below, 2 above, an amplitude of 2 on it. And then the black one is this last one. It has an amplitude of 3. We can see, yeah, it's going all the way up to 3, all the way down to negative 3, amplitude of 3, reflected across the y-axis. Now think of the red one. If I flip this red one, instead of going from 0 to the right going up, it would be if I go to the left going up. I'm going to say it that way. If I reflected this across, what was going up to the right is now going up to the left. And you can see this black one is going up to the left, which also it goes down as I move to the right, etc. So that's what that negative on the x has done. It's reflected it across this y-axis over here. Next page. Question?
A little confused. Just like in my imagination, if you reflect the y-axis and reflect by the x-axis, it looks like the same thing.
You're right. That's exactly right. If I take, here's the parent, which one were we doing up here? Sine? Sine. If I take the parent sine function, looks like this. Didn't put any scale on it, but it's 2 pi right here. So if I reflect this across, I'll do it in black, the y-axis, well, it would be coming up here, doing exactly the opposite thing as that red one was. It would look like that. Now in blue, let's reflect it across the x-axis. So that red comes down here. And this red on the bottom goes up there. You're exactly right. A reflection across the x-axis and a reflection across the y-axis of this looks identical.
But it's not the same.
It is identical in what the graph looks like, but you can do it 2 different ways. I mean, you're doing 2 different things. If I reflect across the y, that's taking this point and that's taking this point and moving it here if I reflect across the y. Now, if I do that with all of them, I got that black graph. If I take this point and reflect it across the x, I get down here, which is just a different point on the same graph. It looks the same. It's reflecting 2 different directions, but it looks exactly the same. In some applications, the frequency, and this is when we do science, when we do physics, we like to talk about the frequency of stuff. The frequency of a sinusoid is an important consideration. The frequency is simply the reciprocal of the period. So if the period formula was 2 pi divided by b, the frequency formula is b divided by 2 pi. Now let's think a minute what period means. It means how many radians per one cycle. Radians per cycle. So frequency is cycles per radian is what frequency stands for, or cycles per something else. So the frequency of a sinusoid, look right there, there's that same formula, it's just reciprocal. It's the only thing when I'm talking about frequency. Sine and cosine work exactly the same way. And then they say graphically the frequency is the number of cycles it completes in a unit interval, like 2 pi. How many cycles does it do in 2 pi? So let's try it down here. Find the frequency of the function. And then it says interpret its meaning graphically. So we'll see if we can graph it out down here. Okay, if I am going to find the frequency formula is absolute value of b divided by 2 pi. So the absolute value of b, can you tell me what b is looking up here?
B is
2/3. 2/3. If I wrote that again, the function is 4 sine of 2/3 x. They wrote it as 2x over 3, 2/3 x. So 2/3 is my b. So 2/3 divided by 2 pi, which means I can take 2/3 and multiply it by 1 over 2 pi. So those 2's would cancel out, and I get 1 over 3 pi. Now, we're going to leave it there. You could go to a decimal, but we like things in radians in the pi. So the frequency is 1 over 3 pi. We have answered what the frequency is. Graphically, how can I do that? Well, graphically, I'm going to use the period of this. The frequency is 1 over 3 pi, which means the period equals 3 pi over 1, or 3 pi. Now, since it is a sine function, I know sine functions start at the origin and they head up. Now, it's going to take a full 3 pi before I complete this cycle. I'm going to go back and look at the parent sine function to know some characteristics so it's easy for me to graph this thing. The sine function starts at the origin and goes up. It takes a full 2 pi before I get back to the same place. Halfway through my period, I'm at 0. A quarter of the way through the period, I'm at my maximum, and 3/4 of the way, I'm at my minimum. Those are enough points to help me sketch this, just those characteristics. So if I take my start at 0, end up at 0, halfway, which would be 1.5 pi, I'm going to be right at the origin. Halfway in between these, right here, I'm at my maximum, and I'm at my minimum.
Maximum will be 4, right?
Maximum is 4. I only went to 1, so let's come back and fix that. Maximum is 4. There's halfway in between those points. And -4, halfway in between those points. So here is, now it would keep going, but they said, sketch the graph in this window from -3 pi to pi. So there's +3 pi. Let me come back to -3 pi. One complete cycle is here. Halfway, I'm in the middle. Well, this is coming down. I'm going to be at -4 there. And I'm coming up to +4 here. There it is. Get your calculators out. Graphing calculator. Hit your mode button and make sure you are in radian mode. Remember, we default all trig things to radian unless they say, hey, do something with degrees. So we go to radian. Y equals, clear out anything you may have there. Let's enter in this equation. 4 sine 2x divided by 3, close my parentheses. Now I want to do some window taking care of a little bit. We need to set our window up correctly. Window, x minimum, -3 pi is what they wanted. -3, I'm actually going to do -3 pi. -3 pi. To x max of 3 pi. 3 pi. My x scale, I want my tick marks to be every 1/4 pi. Because as I notice this one, it seems to be about what I want. Well, let's do every 1/2 pi. I'm sorry, let's do every 1/2 pi. So I'm going to say pi divided by 2. That's going to be my x scale. Y min and max, I'm going to do the -4 to 4. So -4, max of 4, and going by 1, I like that. Now hit your graph button, and it should look just like the picture we just made. There it goes. So there is our graph. Let's see if I already have it. There you go. There's our graph of this function. So you need to be comfortable hand drawing these, as well as entering them in the calculator. But we'll need to have the knowledge in order to hand draw. We have to have all this knowledge, and that's what we're trying to get, is all this knowledge of the characteristics of the graph. Okay, so what do I do when I add or subtract a number onto the x? What does that do? Slides it left and right. These are horizontal translations. In the language of sinusoids, we call them phase shifts. It's called a phase shift when I move it to the right or I move it to the left. And the phase shift is negative of c. Well, we already know that if I add c, it means I'm moving to the left. And if I subtract c, it means I'm moving to the right. So, if I had f of x plus pi, that means it's a phase shift of negative pi. I'm moving left pi. So when we say the phase shift, we actually use the sign in the direction we're really going. A phase shift of negative pi moving to the left. Well, that's what you would tell me if you read this. You would say, oh yeah, I'm going to the left. See if I can spell left. I'm going to the left pi. That's what plus pi right there means. So we call it a phase shift of negative pi. So let's see if we can do that. Getting one sinusoid from another by a phase shift. Write the cosine function as a phase shift of the sine function. Now right here is the sine function. This is the graph of sine of x. Y equals sine of x. That's the sine function. Well, if I want a cosine function is supposed to start here and do this. Keeps on going. Cosine function is doing that. I just color-coded it wrong for you. The black one is the sine, the one they already had, and we are supposed to write the cosine function. The blue one that I wrote is the cosine function, but we're supposed to do it as a phase shift of this one. Well, if I take this point on the sine function and move it to that point, then I've done it.
Pi over.
And what is that location?
Pi over.
That's pi over 2. That's pi. There's 1.5 pi, and there's a full 2 pi to get my whole one cycle in. So I just need to move it to the left, pi over 2. So if I want to move to the left, pi over 2, we'll write it as a nice function. I'm going to say I can take the sine of x plus pi over 2. And I just moved it to the left, pi over 2. This is exactly equal to cosine of x. They look exactly the same. Which is why we call both of these sinusoids, because I can write both of them as a sine function. Let's try the next one. Write the sine function as a phase shift of the cosine function. So right here, this is the cosine function, the parent cosine function. It's starting right here at the top, and then it's coming down, and it takes 2 pi to do one complete cycle out there. Well, if I want to make it look like a sine graph is this. Sine graph looks like that. Now it keeps on going this direction as well. So I can just take this point and move it there. And then it would match up. Everything would just slide to the right. And it's sliding to the right, pi over 2. So I can take a cosine function, slide it to the right pi over 2, and it looks like a sine function. So that's what we're going to do. We're going to take the cosine function, and we're going to move it to the right, pi over 2. And now it will look exactly like a sine function if I do that. Take your calculators. Let's go back to y equals, clear out the thing that you had right there, and let's do sine x. And just look at it, hit graph. So here's my sine graph. Now, I'll let you catch up. So there's my sine graph, just like I expect. Here's the origin, it's rising. I'm going to say y equals, we're doing this, what are we doing right over here? Sine function of cosine. We're doing this one up here, right? The cosine as a sine function. Graph cosine x. That's what I want you to do. Graph cosine x. Cosine x. So we can look at that one. And you notice it's the exact same pattern, but it was to the left. So let's go back to y equals on that sine function, and let's say plus pi over 2. plus pi divided by 2. And now let's hit graph. And we only are going to get one function because they both look identical now. I have made that sine function look just like the cosine function by sliding it to the left, pi over 2. That's what we did on part A, right up here. So, applications. It says one note of caution applies when combining these transformations. If I have a horizontal stretch or shrink, it's working along the x-axis, which also affects the phase shift, which is working on the x-axis. So if I have both of those going on, then I need to be careful how I write it. And here they have shown a good way of writing these where you can distinguish, not only do I have a horizontal change, I've moved to the right h, and I also have a period change with this b right out here. And this way of writing it, with the b parentheses x minus h, keeps intact, or separate I should say, the horizontal and the phase shift. The horizontal left to right translation and the stretch or shrink horizontal. Amplitude, same thing in this formula. Period, same formula. Frequency, same formula. It's just made it easier for us to figure out the phase shift is h, horizontal, left to right. Vertical translation is still k, right here in the end. So nothing else is different on that one. Now notice what they want us to do. They want us to construct a sinusoid that has this period, this amplitude, and it goes through that point. Okay, if I start with this form of the equation, y equals a sine, and when they ask us to write a sinusoid, write the sine one. Even though a cosine graph is also a sinusoid, we write it in the sine form. A sine, I have b parentheses x minus h parentheses plus k. We're going to fill in numbers into this form so that it fits all the things they've talked about right up here. Well, let's start with the period thing. I know that the period formula is, you tell me, do you remember what the period formula was? Has it right there.
A period formula is like 2 pi over epsilon squared b.
So, if I know the period, pi over 5. Period is pi over 5, they're saying. Pi over 5 should equal 2 pi divided by b, and I'm going to have it positive, so I'm just going to write b. B will be a positive value. Easy enough. If I cross multiply, I get pi b. Pi b equals 10 pi. Divide the pi out. B is 10. I now know what to write right here. That's going to be a 10. B is 10. Next thing, they say the amplitude is 6. That one's real easy to fill in.
6.
A is 6. I know what to write right there. A equals 6. Now the next thing they want us to do, they want this graph to go through the point 2, 0. Now normally a sine graph starts here, right at the origin, right? So why don't we just take this point and slide it over to 2, 0, which means I have a phase shift of 2, moving it to the right 2, but if I want to do a phase shift, then I'm going to have a minus 2 right there. H is 2, which would be x minus 2. Well, let's just fill that all in now. My function, y equals a 6. We want an amplitude of 6. Sine of my b, what did we get? 10? Parentheses. X minus 2 to slide it to the right 2. K, didn't need to do anything with k. They didn't talk about moving it up or down at all. So k is 0. Don't need to do anything with it. Now, I'm going to multiply that 10 out. Y equals 6 sine of 10x minus 20. Let's try this and see if it has done what we wanted it to do. So I have 6 sine 10x minus 20. Now I'm going to hit zoom. I'm going to hit zoom, trig, so it defaults to a basic trig window. Choice number 7. Now, you notice anything? Maybe it's like, what in the world is this mess?
It's just like this vertical.
Well, I want you to think just a moment. The period, let's come back over here. The period is 1/5 pi.
Yes.
In 1/5 pi, it has done a complete cycle. So let's modify our window back over here. I'm going to do a minimum of 0. I'm going to start at 0. And I'm going to go to pi. Now think about that. 1/5 pi is 1 complete cycle. That means there will be 5 complete sine graphs in this thing right over here, even though it's really small. Now, amplitude was 6. Oh, my x scale? Sure. Oh, I'll tell you what I'm going to do with my x scale. I'm going to do pi over 5, 1/5. So every mark should be the end of 1 complete cycle. Pi divided by 5. Now I need to go from -6 to +6. And well, maybe we should go to 7. -7 to +7, so we can see it all. Now when I graph it, I should get 1 complete, let me copy this. I should get 1 complete cycle. So if I look right here, there's my mark. I should be right there again. Now I'm not at the bottom, but I'm 1 complete cycle. 2 complete cycle, 3 complete cycle, 4 complete cycle, 5 complete cycle that has happened. Now we never drew this. All we said is we were going to slide it to the right. So I know it looks something like this. I don't have any scale with it. And let's see if right there is the point 2, 0. Let's see if we've been successful in making it go through the point 2, 0. So if I come over here and say trace, let's do an x value of 2. Oh my, it's way off. But there it is, 2, 0. I went through the point 2, 0. My scale was wrong. Let's see, 1/5, pi is 3.14, so yeah, that 2, 0 point is way over here. Is where that 2, 0 point is. Way over in that location. So we were successful in creating something that did what they wanted it to do. Constructing sinusoids. We're doing the same thing again here. Construct a sinusoid, y equals f of x. In other words, write the function. They want it to rise from a minimum value of y equals -5 at x equals 0. Rise, y equals +5 at x equals 0. Rise from a minimum of 5 to a maximum of 25 when we get to 32. To a maximum of 25 when we get to 32. All right? Now, I want to do this using a sine function again. So something with my sine function. Now remember, a sine function usually has the origin is right there. Starting up is a sine function. So I know I have taken this thing and I have moved it so far to the right. Halfway in between those things. I've moved it 16 to the right. So if I'm going to move it to the right, I have x minus 16. I've moved it to the right 16 places. Now, let's come back here. Should have started there, maybe. What does that describe? The amplitude, it's called. And remember, amplitude is maximum to middle equilibrium, right there, the middle of it. 15 to 25. 10. That is 10. which should be half of from here to here. 5 to 25 is 20, so half of 20 is 10. Amplitude is half of that, 10. There's my amplitude. Now, I can slide it. Did I have a period change?
Yes.
I did. I had some sort of period change. From here all the way to here, that's one full period. What's the distance from here to here?
It's double the distance from the maximum to...
Yeah. 32 here, another 32 there. 64 is the length of my period. Now, you remember my period formula? Period equals 2 pi over absolute B. I'm just going to make the B positive. So I'm just going to fill in. My period is 64. That equals 2 pi divided by B. I can solve for B so I know what goes there. Multiply by B. Divide by 64. 2 over 64, I get pi over 32. Pi over 32. If I multiply this out, I could leave it right there. But if I multiplied it out, I'd get y equals 10 sine of pi over 32x minus pi over 2, because 16 over 32 reduces to 1 over 2, 1/2. Pi over 2. Let's try it. See if we can manipulate our window to make it all work, too. 10 sine pi over 32x. Oh, we moved it up. Yeah, we moved it up. Right here we were talking about, that's the middle of it. How high did we move it up? 15. Plus 15. Plus 15. We better, not that. We better take this and add a plus 15 on the end of it. Plus 15. There we go. All right. 10 sine parentheses pi over 32. Pi divided by 32 x. Minus pi divided by 2, close parentheses. Add 15. Now we really need to play with our window after you get this thing all entered in. I'm going to go from 0 to 64. We'll just see one cycle of it for my x's. So when I hit my window, I'm going to go from 0 to 64. I'm going to do my scale of 16. So 16, 32, 48, 64, scale of 16, x scale of 16. Y minimum, 0 is fine. Y minimum of 0. Y max, let's go to 30. So we can see the whole thing up there. And they were going by 5s. We'll go by 5s in the Y scale. Now, if we know what we're talking about, we should get one cycle. There it is, that one cycle, that one blue cycle. We made it work. So if I went to this point right here, it should be 32, 25. I'm going to say trace when my, oh, look at that. X is 32, Y is 25. There it is. We hit that peak with it. Ah, so we are getting educated. We know how to build these things now. Last thing. When we are modeling things that have sinusoidal behavior, if you want to figure out the vertical shift, which is K, if you're using the same letter that they went to switch letters on us here. If you take the maximum number plus the minimum number and divide it by 2, you will get the vertical shift. Let's try it back here. Maximum was 25, minimum was 5. 25 plus 5 is 30, divided by 2 is 15. Vertical shift is 15. If we want to get the period, well, B is 2 pi divided by period. Where did they get that from? Where they got that from is period equals 2 pi over B. So multiply by B and then divide by the period. That's where they got that. I can directly get the B value. Just go 2 pi divided by the period. If I tried it back over here, 2 pi divided by 64. 2 pi over 64, 2 goes into 64 32 times. B is pi over 32. And then it says, choose an appropriate sinusoid based on its behavior at some given time. I like to start at 0. Am I going to choose a cosine or a negative cosine? Well, a cosine graph is one that starts at the maximum and heads down to the minimum. A negative cosine would start at the minimum and head up to the maximum. Or do I want to choose a positive sine or a negative sine graph? Well, I know a positive sine graph starts at the origin and goes up. A negative sine graph would start at the origin and go down. So I just choose the one that fits the situation. We are going to do tides and some calculations from tides. On a particular July 4th in Galveston, Texas, high tide occurred at 9:36 a.m. At that time, the water at the end of the 61st Street Pier happened to be 2.7 meters deep. So I'm just going to say, here's a graph. 9:36 a.m. It was at high tide, which was 2.7 meters deep. Low tide occurred at 3:48 p.m. So at some point later, at 3:48 p.m., I am at low tide. I've gone down to low tide, so I don't know where it is. Low tide is right over here, which happens to be 2.1 meters. My scale isn't real good. 2.1 meters. Okay? So let's assume that the depth of the water is sinusoidal over time, with a period of half a lunar day, which is, they just told me the period. They said the period is 12 hours, 24 minutes. 12 hours, 24 minutes. Well, if I think of this, I'm at high tide, I'll go down to low tide, I keep going like that. I keep going like this. I am going to do this one as a positive cosine graph that I've just moved to the right. Remember, a positive cosine graph normally starts at its peak, and then it heads down like that. So that's what I'm going to do, is write this one as a cosine graph. So let's see if we can begin to fill this thing in. Y equals, I need some amplitude, cosine. Let's start with the amplitude. Well, my amplitude is going to be if I take the difference and divide it by 2. What's the difference between 2.7 and 2.1?
0.6.
0.6, and then take half of that is 0.3. 0.3. There's my amplitude, 0.3 meters. Cosine. Now I need to get my B value. I need to get my B value. Well, remember the B back there was period. Sorry, did it upside down. 2 pi divided by period. 2 pi divided by the period. Now, before we start working with our times, I need to convert these. These are in hours and minutes. I need these in decimal values. 9:36 a.m. is 9 point... Well, I have 36 out of 60, right? 36 divided by 60. What do you get? We're going to do a decimal. We're not going to write the fraction 36 over 60, which is 18 over 30, which is 9 over 15, which is 3 over 5. 0.6. Should have done it in our heads. 9.6. 3:48 p.m. Now, I can't say 3 point something. It's really 15 point something. 24 hours in a day. So it's kind of like military time. This is 0 at midnight, and then it's 903 p.m. is 3 hours after 12, which is 15. So it's 15 point. What's 48 divided by 60? 0.8. And my period, I need to do the same thing too. 12 hours, 24 minutes. Well, that's really 12 point, what's 24 out of 60? Was that 12 over 30, 6, 15, 2, 5, 0.4. 12.4. So I can say, My b value is 2 pi divided by 12.4. Let's get a decimal approximation. We'll go to 2 places. Point 0.51? 0.51. 0.51. So there's my b, 0.51. X, I'm moving it to the right, minus, and I moved it to the right how far? 9.6. I moved it to the right, 9.6. 9.6. Plus, now I moved it up, right here is the middle.
It's 2.7 plus 2.1 divided by 2.
4.8 divided by 2, 2.4. I moved it up 2.4.
That's the formula.
Now, that's the formula. I could multiply it in. Let's just leave it in this form right over here. Let's enter it in our calculators. So y equals cosine. Sure you get enough parentheses there after that cosine, because we didn't multiply this one in, so we still have double parentheses there. Now we want to manipulate our window before we try to look at any graph. So if I make this fit some of the scale that we have back over here, I'm going to, on my window, I'm going to start at 0. And, well, let's go through 24 hours in the day. Should we do that? Let's go through 24 hours. That would be one day. And my scale, oh, I don't know, maybe 4. Y minimum, 0 is okay, because we don't ever go to 0. 2.1 is as low. And max, sure, 3. Y max is 3 by 1. So that'll work for me. So let's look at a graph. This should be the graph of the tide. Now let's verify. If I put in an x value of 9.6, I should get a maximum of 2.7. So if I hit trace and hit 9.6 in my x, y is 2.7. There it is. Okay, let's answer some questions. I'm going to change my window to make the y go a little higher because I'm kind of covering myself up. So I'm going to hit window and I'm going to do my y max of 5. Simply because I want to be able to put it in the middle of my picture. So let's see if we can answer some questions now. It says, all right, at what time on the 4th of July did the first low tide occur? Well, my first low tide is going to be this first low spot. That's a minimum spot on my graph. So I'm going to hit my calculate and say, find me a minimum. And my left bound on that minimum, oh, my left bound is going to be 0. And my right bound is going to be 9 because it was high tide there. My guess is 4. It'll find it for me. There it is. Minimum occurred at 3.44. Now, x equals 3.44 is at 3 what time? This is 0.44 of 60. What's 0.44 times 60? Put it in the calculator. Okay. 0.44 times 60. Because it's 44 hundredths of 60. Say that again.
26.4.
Okay, 3:26 a.m. It's really 3:26.4 a.m., but 3:26 a.m. That's when our first low tide occurred. Why does that say 3.40?
Because we maybe use the approximate 0.5.
Maybe it's a rounding thing is my guess. What does the book say? Let's get the right one. So I'm going to keep the right one. At 3:24 a.m. We got 3:26 a.m.
If we just we approximate the b.
We approximated the b value as the difference. They left it pi divided by 6.2. They didn't round off the b value. There you go. That's where the difference came from. We'll go with this one, since we're working with this one right now. What was the approximate depth of the water at 6 a.m. and 3 p.m.? How can I find that? Well, at 6 a.m., that would be 6. X is 6. If I just hit my trace and get an x value of 6, it says, oh, 2.32 meters deep. This one will probably be just a little bit different. No, 2.32, it's not even that different. And then they want to know at 3 p.m., well, that would be 15. So if I do an x of 15, it's 2.12. So 2.12, where do we go? There we go, 2.12. That's how deep it is at. What was the first time on July the 4th that the water was 2.4 meters deep? When is the first time it hit exactly 2.4? I'm going to go y equals and put 2.4 in so that I get my graph that includes, there's that depth. When is the first time? It's 2.4? Probably back here. I am going to calculate an intersection, choice 5. First curve, the cosine, second curve, the 2.4. My guess, 0.1. I think it's really close. 0.36. So 0.36 times 60, it's going to be real early. Theirs is 0.31 instead of 0.36. If I took 0.36, theirs is slightly different because, again, of rounding. If I take 0.36, well, what's 0.36 times 60? 21. So 22. So at 12:22 a.m. That was the very first time, since time 0 is midnight, 12 o'clock. There you go. Sinusoids. Anything that's periodic, we can model with sinusoids. It gets really exciting.